Hi, I hope this video is going to help you understand dot product and cross product again better, because I'm going to explain how they both come from multiplying quaternions, which are four-dimensional numbers. You don't need to know about quaternions, but I think knowing a little bit about them helps you understand dot product and cross product. It's also the case that quaternions today are quite widely used, so you may have to learn about them later. Okay, we have dot product and cross product, and teachers emphasize these are very different things. So the dot product is just a number. It's not a vector. You multiply together two vectors and you just get a number. It's like, two tigers having a baby and it turns out to be a rabbit. And if the two vectors are perpendicular, then it is 0. It's 0 if they're perpendicular. The cross product works differently. Firstly, it's a vector. It's two vectors give you a vector. Secondly, that is 0 if they are in the same direction, not if they're perpendicular. So you have two multiplications here, which seems a bit much. They work very differently, and also they're both rather strange multiplications. They don't work like multiplications of ordinary numbers or multiplications of complex numbers or even multiplications in matrices. A lot of the rules that work for those other multiplications just don't work here. In the case of dot product, you multiply together two vectors, you don't even get another vector. You get an ordinary number. On the other hand, although they're very different, when you look at these two formulas, mod R1, mod R2 cos theta, and mod R1, mod R2 sine theta times a unit vector perpendicular to the two vectors you're multiplying, those two formulas, I think there has to be some connection between them. And in fact, there is. And it's that they both come from the quaternion product. Quaternions are four-dimensional numbers, just as real numbers are one-dimensional numbers. Complex numbers are two-dimensional numbers, and quaternions are four-dimensional numbers. It turns out that it's impossible to define three-dimensional numbers. And quaternions work mostly like one-dimensional numbers and two-dimensional numbers, but there's one particular rule that works for one-dimensional numbers and two-dimensional numbers, which breaks down for four dimensions, which is the order of multiplication matters, as it does with matrices, but in a different way with quaternions. So, a quaternion, so if I called a quaternion R, it would have a real part, and it would have three imaginary parts. Right. I, j, and k are three square roots of minus 1. Minus 1 has three separate square roots in quaternions. So I squared is minus 1, and j squared is minus 1, and k squared is minus 1. How do you multiply together I, j, and k? You draw a little circle like this, and clockwise you come to the next one. So jk is equal to I, ki is equal to j, and ij is equal to k. But if you go in the opposite direction, you get a negative result. So kj is equal to minus I, ik is equal to minus j, and ji is equal to minus k. This looks a bit like, in fact it is exactly like, the multiplication table for cross products of unit vectors. What you might like to do now is to work out what's ijk come to. Pause the video and work it out. Yep, you worked it out. That's -1. Right, those rules tell us how to multiply together two quaternions. And for these purposes, we're going to be bothered really with quaternions which are all imaginary, which have no real part. So let's take two quaternions. R1 is x1i plus y1j plus z1k, and R2 is x2i plus y2j plus z2k. Those are two quaternions which have no real part. We're going to multiply them together. The rules which we've set down about multiplying I, j and k tell us exactly how we have to multiply this. So maybe pause the video and work out the multiplication. Yes, R1, R2, it has a real part, which is minus x1, x2, minus y1, y2, minus z1, z2. And for the I term, it will have y1, z2, minus y2, z1, i's. For j's, it will have x2, z1, minus x1, z2. And for k's, it will have x1, y2, minus x2, y1. Now that's quite long, but it also looks quite familiar. And we can put it in other terms that we know. So, I want you to pause and think, firstly, what does that look like? Secondly, what do these terms look like that you're familiar with? Pause and see what you think they are. Right, the answer is this is just like a dot product. So that is minus R1, R2. If R1 and R2 are vectors which sort of correspond to, which are sort of cousins of these quaternions. So the vector R1 is that, and the vector R2 is that. So they're, as I say, they're sort of cousins of the quaternions. And what we get here is a determinant. Right, well, there we go. What, and where the cross product and the dot product come in is that this is minus the dot product plus the cross product, as long as we reinterpret I, j and k as the unit vectors. So the dot product and the cross product are both parts of the quaternion product. Now, that fact explains a whole heap of things. It explains, firstly, let's rub this all out. So we've got R1, R2 as the quaternion product is equal to the vector dot product minus the vector dot product plus the vector cross product, as long as we reinterpret that vector cross product to be a quaternion. Okay, firstly, this will explain why the triple product works the way it does. If you've got three quaternions multiplied together, think what is the, so this is going to be right, it's going to be like that. Think what is the real part of that multiplication going to be? Well, the R1, remember R3 is all imaginary, like R1 and R2. So that times that is going to be all imaginary because this is just a number. What are we going to get here? We've got I, J, K, X1, Y1, Z1, X2, Y2, Z2. That determinant times X3I plus Y3J plus Z3K. Now, what we're worried about here is the real parts of it. So this is the real part of R1, R2, R3. We said we can ignore that if we take the real part is that you're just going to get when the I multiplies by the J multiplies by the J, the K multiplies by the K. I times K, J times K, and so on are all going to produce imaginary bits. So this real part, just pause and work it out. Okay, the real part comes to this determinant, and then if we just do two swaps of rows, we see this is X1, Y1, Z1, X2, Y2, Z2, Y3, Z3. So, what we have here is the formula for the triple product of the matrix of the vectors. The triple product of the vectors is the real part of a triple product of quaternions, and it's equal to that determinant, and that tells us also why in this triple product you can suddenly start swapping around the you can start swapping around the dot and cross products. You can just change the order of the multiplication. That's the only way I think you can understand that is understanding how both multiplications come from quaternion multiplication. We're going to stop there. There are a couple more videos on this post which will tell you a bit more about quaternions if you're interested. It may help you understand cross product and dot product better. It may make it a bit less like hocus pocus, and it's quite interesting anyway.